welcome back. Part 2 of the basic integration or basic antiderivative rules. So we learned a few rules in the previous video. What I want to do now is step it up. That is, if we have the integral of 3 over x squared dx, how does one find the antiderivative of that? Remember, this is the derivative expression. Where did it come from? What is the original function? Well, my friends, we have to do the same thing we did before. We have to think about this as a power rule. That is, there is no fraction rules for integrals, okay? There are no fraction rules for integrals. So we'll have to rewrite it. We have to get really good with our algebra skills if we want to be really good with integration. So I'm going to rewrite it. Remember, denominator comes up, negate the exponent. Beautiful. Hey, that's the power rule. What can we do with the constant? Just put it in front. It's a constant. Keep it in front. So really, that 3 is just there for the ride. This works in this rule. My n is -2. All right, my n is -2. The rule for integration is to add 1 and divide by that number. That is the rule for integration. Again, whatever your power is, add 1, divide by that number. We're doing the opposite of the derivative here. Keep that in mind. This is the antiderivative, the integral. So we got to go backwards. And so we are left with this expression, which, okay, 3 over -1, when you multiply that out, is -3 x to the -1 plus k. We can rewrite this as -3 over x plus k. And so that would be in my original function. And if you take the derivative of this as a check, right, the derivative as a check, so we got to pause. Bring the -1 down to multiply, -3 x to the -2. That matches. If you take the derivative, you'll get there. We are now going backwards. That's what we're doing. See, this was the original function, power rule and exponents, derivative rule, and here we are, clean it up, right? So original function, exponent, derivative rule, that direction. We're now going backwards. We're now undoing the derivative when we do the antiderivative. We're going backwards. So this is the original function whose derivative is that. And that's really what we're working on is, if this is f prime, what is f? If this is y prime, what is y? If this is dy dx, what is y? If this is marginal cost, what is cost? We're going to work on applications down the road, see future videos. Right now, I just want to be able to integrate anything, at least according to the power rule on the board. There are other techniques I'll teach you soon, but right now, I want to be able to see a power and just destroy it. So be careful. When the power's in the bottom, bring it up by negating it. Another sneaky one is, what if the power's in the top and you have a constant in the bottom? No big deal. This is the same thing we do with derivatives. We play around with constants by kicking them out. That is, we kick this constant off the top as 1 over 100 x cubed dx. So that's the first pause. You have to see good algebra. X cubed over 100, that's really a 1 over 100 that's inside. Let me kick it out. Any constant can be kicked out of an integral, just like you see. That's part of the constant rule. Can I integrate that? Heck yeah. There's my power. My n is 3. So the antiderivative would be add 1, so make it 4 and divide by that number, plus some constant. Again, the antiderivative is always add 1, divide by that number, because we're doing the opposite of the derivative. Clean this up, you betcha. X to the 4th over 400 plus k. And again, why plus k? Well, because the derivative of 80 is 0, and so it disappeared. The derivative of 92 is 0, so it disappeared. So when we do the antiderivative, I got to make sure we understand there could have been a constant. That constant could be 0. When we look at applications, we'll try to figure out if we can exactly find that constant for specific applications. But right now, again, today's mission, here's the derivative. Where did it come from? The antiderivative. And really, as long as I can write it according to that power, I'm just going to hit it with that power rule over and over. The only one I'm not going to touch today is -1. That's a very special video when we look at logs and exponentials. We'll look at that. All right. So that's trick number 2. It really comes down to constant in the bottom, kick it out. constant in the top, move your variable up top by using exponent rules. And we can put these all together in, for example, cube root of x minus 32x to the 8th plus 14 dx. Whew, nasty one for this example. And in fact, let's make it nastier. 8.1 will be my exponent. Because honestly, I don't care what the exponent is, as long as it's not -1. If it's -1, please, again, see the log video. That's what the thing is. As soon as I see -1, flashcard, -1, antiderivative of -1, there's got to be a log in there somewhere. We got to work with that. Right now, we're doing integrals, and I'm not worried about the -1 exponent. I'm doing integrals. So how do I do this? Well, let's really take this example and take our time with this example. At any minus or plus, you may split it into separate problems, and I would do that. And when you have a cube root, let's recall, cube root is a particular power. So I'm pausing for that dramatic effect. The power I'm looking for is 1/3. Please review, right? Square root, 1/2 power. Cube root, 1/3 power. Fourth root, 1/4 power. You're getting the idea. So what I said was that any minus, we can split it into 2 separate problems. So that's a problem, boom. This is a problem on its own. And in fact, I also said, if there's a constant in a problem, you can kick it in front of that integral. So that 32 goes in front of this special integral just for x to the 8.1. Please notice, this is very important. I did not put that in front of the x to the 1/3, that cube root. It's not there, right? That 32 is attached to this thing. So that 32 should still be attached to this. That's very important. A lot of people like to push it out way out there. You can't do that. You can only push it out in front of the integral that's next to the variable you're dealing with. And at any plus, you can have a separate integral. So this is important. We're doing a bunch of rules in this one. This is a nice, pristine example to really take your time. What you should do is go back, pause it here, and try to do it on your own. For each one of these, that's really what you should try to do, is pause right there and try it on your own, and then go and see if you can do what I've done. You see the work in front of you. Try to flow through the work. So this is an example. What I would do is at any minus or plus, I'm distributing the integral for linear pieces. Awesome. At plus and minuses, you could do that. Now, if there's a constant, so there's like an S there, an integral sign. So there's a constant. I can pull the constant in front of that integral sign, and that's what I did there. Now, I notice I have a power of n. I'm going to use the power rule. I have a power of n. I'm going to use the power rule for integrals. I have a constant. I'm going to use the constant rule for integrals. And then I will be done. So, all right, just got to be careful. When you take the antiderivative, the integral, you got to add 1. So fractional math time. When you add 1 to 1/3, again, adding 1, you go to 4/3. If you need, you got your TI calculator. 1/3 plus 1 is 4/3. And whatever you add to the exponent, divide by that number, because that's the rule, minus, add 1 to the exponent. Now it's 9.1, because when you add 1 to 8.1, you get 9.1. That's what happens. And divide by 9.1. Last but not least, 14 must have came from 14x. And last but not least, there is some constant there. Because again, if that was 600 at the end, the derivative of 600 would disappear and you wouldn't have seen it no matter what. If that was a minus 14,000, the derivative of 14,000 is 0 and you wouldn't have seen it anyways. What I like to do to make sure my answer makes sense is just check it. The derivative of 14x is 14. Nice. The derivative of this, well, the derivative rule is bring the power down. When you bring it down, the 9.1s cancel. 32x to the subtract 1, 8.1. Nice. Over here, when you bring the power down, the 4/3 cancel. All right, when you bring the power down, the 4/3 cancel. You're left with x to the 1/3. A beautiful antiderivative right there. How much do you clean it up? Talk to your professor. You can flip and multiply and make that 3/4 x to the 4/3. And you could divide these two and give some fractional, decimal, whatever you're looking for there. but I'm happy with the way it looks at this moment because I really want to make sure you get to the fact you could deal with any radical, you could deal with any exponent, barring the -1 right now, and you deal with any constant. This problem really breaks down all the basic rules of adding, subtracting, and power rule. Thank you guys for watching this video. I look forward to you guys seeing me in the future.